Hey guys, it's Miss Kopek. I'm here with a lesson for the 8th graders. So today we are going to go over using the laws and rules of exponents to solve problems. So that will help you with this page right here, but it's also going to apply on the pages where we're doing scientific notation. So if you still have your notebook from the beginning of the year, we did make this foldable way back when with the different rules of how to handle integer exponents, but I thought we'll just go back over it today as a review. Okay, so the first thing, what is an exponent? An exponent is the little number that is written as a superscript, which means the little tiny number that's up high next to the number, and it tells you how many times you're going to multiply that number by itself. So, for example, this means 4 times 4 times 4. 4 times 4 is 16. 16 times 4, I don't know offhand. I'm going to cheat and use my calculator. 16 times 4 is 64. So 4 to the third power is 64. When I'm entering this into my calculator, there's a few different ways to do that. So let's go over that really quick. So I would do 4 to the third power. And I always move it over to make sure it's okay. And then hit enter. If you are using a calculator like this, clear that out. Same thing. 4 to the third power, enter. If you just have a handheld calculator like this, the little cheap ones like that, which is fine, but there's no shortcut for it, so you would just have to do 4. Turn it on first. Let's see. On 4 times 4 times 4, and just count how many times that you're doing it. This does not mean, no, I don't want to see this. It does not mean 4 times 3. That's the most common mistake. The answer is not 12. It does not mean 4 times 3 is 12. It means 4 times 4 times 4 is 64. Now, when I have a negative exponent, I don't ever really want to leave it like that. And a negative exponent means that I have to take the reciprocal or the flip, but keep the absolute value. So, for example, 3 to the negative 5th power would become 1 over 3 to the positive 5th. 1 over a to the negative 2nd power, well, I'd flip that, and this would just become a to the 2nd power, or a squared. Here, I have both of these have negative exponents, so I'm going to flip that one down there, and that one, since it's also negative, gets flipped up there. So this becomes 3 to the 7th power over b to the 3rd power. Now, if I'm solving problems where they're asking me to apply the rules of integer exponents, or just I think the worksheet calls it the laws of exponents, I can't really do anything with adding and subtracting. The only thing I can do is follow the rules for collecting like terms. So, for example, 3 squared plus b to the 5th, different bases, different exponents, can't do anything with it. The only thing, I can't simplify it at all, so that would just have to say 3 squared plus b to the 5th. Now, b squared plus b to the 4th, I might be tempted to think that I could do something with this because they're both b's, but when I'm talking about like terms, they have to have the same base and the same exponent in order for me to do anything with it. So this I also can't do anything with. That would just have to stay b squared plus b to the 4th. I can't simplify that any further without having more information. However, here I have b to the 4th and b to the 4th. I have 2 b's to the 4th, which would be how I can simplify this using the rules for collecting like terms. So that one I could simplify a little bit, but only because it has the same base and the same exponent. Now, if I'm multiplying, the shortcut would be that if I'm multiplying and the base is the same, I can add the exponents. So here I have 2 to the 9th power, 2 to the 9th power times 2 to the 7th power. So I'm thinking, I'm taking these exponents and I'm thinking 9 plus 7 is 16, and that would simplify down to 2 to the 16th power. Now, don't forget your rules for adding and subtracting with integers, though. So here, I'm thinking I have a to the 5th plus a to the negative 8th. So I'm thinking 5 plus negative 8, and I can either use my calculator and do that and get negative 3, or I can think opposite signs, subtract, keep the sign of the larger number. I know that my answer is going to be negative 3, so this becomes a to the negative 3rd. But going back to my rules of negative exponents, I know that I can't leave it like that, so I'd have to change it to 1 over a to the positive 3rd. Now, why does that work? So let's take a look at, let's do b to the 3rd power times b to the 4th power. Now, when we talked about what an exponent means, we said, I'm going to get a different marker, I don't like this one. I said that b to the 3rd means b times b times b times, well, and b to the 4th means b times b times b times b. So let's see, I have a total of 1, 2, 3, 4, 5, 6, 7 b's, so that becomes b to the 7th power. I added how many b's I had there and how many b's I had there, and I got 7. That's why this rule works. Let's continue on. And I'm going to start trying to upload copies of these notes to Jupyter. I just haven't quite gotten there yet. I'm still trying to set up the home classroom. So bear with me. I'm trying to get it together. So division, when I have division and the base is the same, I'm going to subtract the exponents, keep the base. So here I'm going to be thinking 7 minus 5 is 2. So 7 minus 5 is 2. So a to the 7th power divided by a to the 5th power becomes a to the 2nd power. We don't typically see it with that sort of division sign. Usually we see it written as a fraction. Remember, don't get confused about these negative numbers. I'm thinking negative 2 minus 10. Well, I know that that's negative 12. So this becomes b to the negative 12, but I can't leave something with a negative exponent, so I have to now do 1 over b to the 12th power. I don't ever want to leave a negative exponent in my answer. That's not a complete answer. Now, sometimes you'll see things like this. Well, I can't do anything with this a to the 5th because that is a different base, but I can do something with these c's here. I have c to the 3rd and I have c to the 5th. So I'm going to subtract, so I'm thinking 3 minus 5 is equal to negative 2. So I can start by just rewriting that as a to the 5th times c to the negative 2 power. But again, I can't leave that there, so I have to simplify it by moving that c to the 2nd power down below. So it becomes a to the 5th over c to the 2nd power. Now, why does this work? So let's use this problem that we started with as an example, but let's rewrite it as a fraction. So we have a to the 7th over a to the 5th. Well, I know that a to the 7th really means a times a times a times a times a. 1, 2, 3, 4, 5, 6, 7. 7 a's multiplied together. And that a to the 5th means a times a times a times a times a. Now, a divided by a is 1. We cancel those out, just like how when we're doing an algebra problem, when we have the same number up and down, we can cancel it out. So that cancels out, that cancels out, that cancels out, that cancels out, that cancels out. I'm left with 2 a's. So my answer is a times a, which simplifies to a to the second power, or a squared. That is why these shortcuts work for division. The other thing that you'll sometimes see is what does it mean to have a power to a power? So sometimes when we're talking about something with an exponent, we say taken to a certain power. So I could say d to the third, or I could say d cubed, or I could say d taken to the third power. So when I have a base and an exponent, and both of those are taken to a power, and normally you'll know that both of them are being taken to a power because you'll see these parentheses there. You want to keep the base and you want to multiply the exponents. So here I have d to the third taken to the fifth power. So I'm thinking 3 times 5 equals 15. Should have left a bigger bubble there. So this becomes d to the 15th power. So there's two, I think I might have made this one more complicated than I needed to. So we'll come back and solve this one in a minute. That was a bad example. Okay, let's do this one though. So when I have it here and here, I go and I distribute this to both of those. Think of it like distributive property. So I'm thinking both 4 times 10 and 3 times 10. So this becomes g to the 40th power over h to the 30th power. All right, so let's explain why this works, and let's use this problem here. So let's say d to the third to the fifth. So what does d to the third mean? Well, that really just means d times d times d. Taking that to the fifth means I'm taking this whole thing and I'm multiplying it by itself 5 times. So here's 1 time, d times d times d, 2 times, d times d times d, 3 times, d times d times d, 4 times, and 5 times. If I count those all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I have d to the 15th power. So that's why this shortcut works, because I'm taking how many d's I have there, or whatever number or variable I'm using, and I'm repeating that, using repeated, and then I'm repeated addition, adding 3 plus 3 plus 3 plus 3 plus 3, and so that's the same as multiplying 3 times 5, which gives me d to the 15th power. All right, so let's go over these special cases. I didn't forget about this one, but we're going to have to do that one on another page because it's a little bit more complicated than I realized when I was writing that. Okay, so to the 0 power. So let's see, any number that's taken to the 0 power, and any variable for that matter, anytime you see anything taken to the 0 power, it equals 1. So a to the 0 power is 1. 7 to the 0 power is 1. This whole complicated thing taken to the 0 power is 1. Anytime I see anything taken to the 0 power, it's 1. And I'll explain on the next page why that works. But let's go over the other special case, which is the power of 1. So any number that's taken to a power of 1 is equal to itself. So for example, this is just saying I'm multiplying 25 by itself 1 time. So that equals 25 times, oh, I already did, just 25. Same thing, z to the 1 power becomes z. Similarly, anything that I have, let's say z to the negative 1 power, well, that just becomes the reciprocal, 1 over z. All right, so let's do that.